Alright, we're on the air. Okay, good good morning actually. It's still before 12 p.m., I guess. So, good morning or whatever time it is in a place. My name is Bernardus, and today we'll be talking about the JVM architecture and the magic behind write once, run anywhere. So yeah, we finished C 2 weeks ago actually. Last week I spent it all on setting up my local to set up my computer so it can run Java smoothly. I installed Android Studio. I installed IntelliJ. Tried connecting it to the Windows subsystem for Linux, and yeah, so this week I will be talking about the JVM architecture and the magic behind Write Once, Read Anywhere. As you can see, I only wrote 2 notes in 2 days because this week was pretty busy after all. I got midterm exam from Monday until Friday, and then on Saturday I went on a school organization trip and I just got home yesterday from the trip, and you know what I'm talking about. So without further ado, let's get started. So documentation of Java Virtual Machine architecture and the magic behind WORA Day 1. So we all have heard that Java philosophy is write once, run anywhere. So what do you think about Java? Is it enterprise, stable, or maybe verbose? The interesting part is that any Java code can run quote unquote anywhere. How? It is because of the Java virtual machine. In C or other compiled languages like Rust, yes, you get an executable for like .out or .exe or even .deb, which won't work in other operating system. Let's say I compile my C program for in Windows. Specifically, I targeted Windows. That same executable won't run on Linux distros. So this is the what Java means by write once, run anywhere. In Java, you can get those because of the Java virtual machine, which we'll explain later. But for now, you shall know the Java programming language and OpenJDK. So in a language, there is what we call the language itself and the runtime, not runtime actually, like the compiler or runtime management or the runtime. Sorry. There are languages and there are compilers and runtimes. Those three actually are separate things. You have the C language and GCC and Clang compiler. For Java, there are similar instances for the just-in-time compiler. So these 1, 2, 3, 4, 5 are part of the Java ecosystem. They have their own types and they have their own explanation. Let's get first into the OpenJDK. It is a tool chain, the same as you installing build essentials for C, and then you get GCC, make if I'm not mistaken, and etc. In Java, installing OpenJDK is equal to installing all the stuff you need for Java development, minus the integrated development environment, of course. That stuff you need to configure yourself. OpenJDK is just one of many toolchain implementation. There are Oracle's JDK, Amazon's JDK, etc. So OpenJDK basically it's like one packet for all. You install this one and then you get the compiler, the launcher, the JVM, the hotspot compilation inside the JVM, etc. So that's basically it. These three are what's inside the JDK. One of them is JavaC, JVC or JVC, yes. Yep, compiler. But isn't Java a just-in-time compiled, and people say it's interpreted and compiled? What do they mean by that is that Java is interpreted at first, and then as the program goes on, the frequently executed code will be compiled into highly efficient machine code. So as I talked about in undefined behavior, in the just time compiled, it's the same as interpreted by code and virtual machine, the same as interpreted, but the differences lies in runtime. A just-in-time compiler turns frequently executed parts or hotspots in Java into native machine code, combining the best of compiled and interpreted languages. Java compiles your source code into intermediate language called .class. This is the equivalent of basically, yeah, not really the equivalent because this one outputs the executable. But what do I mean by this is that it compiles your .java into .class code, which is like the intermediate language before your compiler, before the interpreter runs it off. Okay, then we have Java. This is the launcher. So in C, if you call .a.out or ./main, in Java, after you compile .java into class, you call Java main without .class. To launch a Java virtual machine process, and load it into memory. So basically, it turns your .class into a living process inside the Java virtual machine. What do I mean by that? I'll explain it later, but for now, know that one. So next, a plot twist in Java 11 allows you to run directly Java main.java without compiling it first with Java C. This is the same as GCC. What did I write, bro? What did I write? Okay. Should look pretty nice right now. Yes, GCC output main.c, and then run it immediately. But the class is stored in memory, so in RAM, not disk. So that's the same as that, immediately running, but without writing the class in the intermediate language into the disk. So we got the Java C and launcher out of the way. Then we have the JVM. It is a virtual machine. Remember, a virtual machine. It'll be important for later. This is the service transaction, honestly. But in short, JVM is like the translator or interpreter just compiled of Java. It takes .classes files and then translates them into machine instructions, simultaneously handling memory or garbage collector and pointers, etc. So that's it for the part of the OpenJDK ecosystem. There are a bunch of more. Probably there is more than this, but this is what's important, alright? And then we have Maven and Gradle. What are these? These are build tools. It's just as painful to type many.c files to GCC as it is with Java. So basically, Maven and Gradle are just build tools for Java that handle a big folder structure. So let's get straight into Maven and Gradle. So you're tired of entering every .c file into GCC every time you change something? Yep, that pain also exists in Java. Luckily, we have Maven and Gradle. Their functions are the same. Compile all .java source code, link .class files, and run them. You just write the coordinate like group, artifact, and version in a file. Maven is the old school one. It uses XML, very rigid and stable, and it is labeled the old way. And then we have Gradle, basically the same. They talk to the same Maven central repository, if I'm not mistaken, and then uses a script, Groovy or Kotlin, called build.gradle. It is faster and more flexible, and it is the new default for Java and Kotlin development. However, they also help you install dependency, as in Java, you don't have a universal package manager like NPM. When you run mvn install or gradle wrapper build, the tool reaches out to a server called Maven Central and downloads the .jar files you need, puts them in a local cache, and links them. So that's basically for Maven and Gradle. Now we'll dive deep into the Java Virtual Machine internals. So an analogy to help it stick faster. Java apps are like Electron. When you have an Electron app, you bundle Chromium and web technologies for each app. The same with Java and JVM. However, it is not as severe as Electron, as JVM is already very optimized, and the JVM gets stripped down to the absolute bare minimum for your app's need. So that's basically for Java Virtual Machine Internals. We'll dive deeper to the memory section, garbage collector. So as we talk about in virtual address or memory, so each JVM process is the same as an OS process, with the difference being that inside that process, it has a JVM, so every Java app is just an instance of Java Virtual Machine. And that class files are data, actually not data on the process heap if I'm not mistaken, but it'll get explained later if I'm not mistaken. Yeah, being translated by JVM in real time on the fly, except for hotspots. JVM process internals is divided into two specific zones for process run by JVM. Sorry, not two specific zones, but rather three. It has heap, stack, and the method area, basically the same as .text and .data segments. So before we dive deeper, I talked about Electron, right? So what does that mean? So each app basically is just an instance of Java virtual memory. So let's say I have a Java app, it's running Java virtual machine. And remember the name, it is a virtual machine. So basically, it's like a mini operating system instead of that. Not operating system, but a virtual machine. That's the more correct implementation. And your codes are processes run inside this Java virtual machine. So it's a nested process. Your operating system only sees a JVM instance, but inside that JVM instance lives your processes. So that's basically it for Java Virtual Memory. The heap. Java processes internal. Welcome back, heap. Yes, basically inside the process, inside JVM. So basically the processes inside the JVM, your codes, you have a heap created with new goes here. Just remember that this is the heap of the process inside the JVM, not the JVM processes heap. Remember also, JVM is a virtual machine. It's a small OS process. Inside JVM runs your processes, garbage collector, interpreted, just-in-time compiler, and your .class files. The memory of your own process, .class files, is being translated directly to real OS memory by the JVM. And speaking of garbage collector, you don't do pointers in Java. Free, malloc, it's the garbage collector job to do so. It's a background thread that cleans unused variables and data objects. So yeah, now you should remember about mutex. That's what we talk about in processes and threads. That's basically it. To avoid removing data while it is still used, there's an instance of stop the world. Basically, the name is stop the world, yes. So basically, to move objects, update reference, all other threads will be stopped first. This is what we call stop the world moment. However, it's not a single global mutex. For most objects that die young, it's placed in the younger generation. The garbage collector cleans this area frequently and barely noticeable by human eyes. It is only a few milliseconds. However, if an object survives several cleans, it is promoted into the old generation. If this gets full, the garbage collector will perform a full garbage collector, which creates stutters. And we have the Java Virtual Machine stack. Do I even need to explain this? A stack is basically used for like a nodes for each thread to do something. The same as each thread having its own stack, it's the same as it is in Java. No explanation needed, as we have talked about in process. Then the method area. This sounds fancy until you know it's just the same as text and data segments. It stores class structures, method code, and static variables. And then inside this we have the just-in-time compiler. This is the translator inside the Java virtual machine. It has two gears. The interpreter, this starts immediately after your dot classes are passed into the Java virtual machine. The interpreter runs your code line by line, the same as you do in Python. And then the spicy part, why Java is so efficient and used in many enterprises is just-in-time compiler. Now we get to the part where Java is efficient and faster than VM-based interpreted languages. Just-in-time compilation. As its name suggests, just-in-time, as your interpreter runs, the just-in-time compiler watches. Are there any sections or functions running many times? Then, if there's one, it will be marked as a hotspot. Then the just-in-time compiler compiles this specific function or section into a highly optimized native machine code 86 platform or IRM platform and caches it. So yeah, that's what makes Java so efficient and fast. Not Java only, but all just-in-time compiled languages like C#. Now, if a specific machine code is unsafe, because the just-in-time compiler likes to do optimistic optimization compilation and crashes during production, the app won't crash. Instead, the just-in-time compiler will decompile the unsafe part and return to safe interpreter mode. This is called the optimization. As I explained, this is why just-in-time compiled languages like Java and C# and etc. so efficient for long-running enterprise and banking software. Hotspot compilation. They can adapt to runtime and production surprises by using interpreter mode and can nearly reach compiled languages speed in the long run because of just-in-time compilation. So that's day 1 for ya, and then we move to day 2. I've returned from Indonesian and yes, I literally forced myself to learn Java internals in the middle of a midterm. Forgive me, but yeah. Actually, the Indonesian and civics are quite easy exams. The hard one are history and PE. Oh my god. Yes, I also have a preparation for a way of the cross. So let's get this finished as well. I finished it, just I'm lazy. Java. So an analogy for you. Java takes a lot of weight off your shoulders to put it on your legs. What does that mean? In C, you manage memory manually. You do free, malloc, and getting user input must have a buffer size. You need to set the maximum and encode the edge cases of memory yourself. Powerful, but you can shoot your foot. In Java, the mindset is different. They take a lot of weight off your shoulders during development time, no guessing memory size, handling edge cases. Java has try catch throw finally for graceful error handling, and it'll throw an exception, no undefined behavior at all. No undefined behavior at all. But it puts the weight on your legs. It's just-in-time compiled, unlike C, which has ahead of time compilation. So the weight is put during production. Even though Java is efficient, it's not as fast as C. So you're sacrificing runtime performance for developer experience during the development time. But it's not as severe as we talk about. Java is just in time compiled, so it can quote-unquote nearly reach C performance. Not as fast, but nearly reach in some cases, not all cases, alright? And then we get this, we have stick this analogy, then we move into Java primitives and object. So now remember that we studied about pointers. So after this, we'll be talking about C features that gets translated into Java. We touched Java, right? Yes, primitives are essentially the same as data types in C. You would encounter types such as integer, char, float, and double, among others. And as a note, Java is an object-oriented programming language and doesn't have a struct type. Primitives are the same as they are in C. They can live on the stack, heap, or the method area. As a side note, the method area I mean is static and global variable, not the yeah, it's the same. They can live on the stack. By default, they can live on the heap using new keyword, and they can live on the method area. However, for object, basically every data type that starts with a capital letter, including your main objects, is a stack pointer pointing to a set of data on the heap. This is also what's called Java references. So I have this code right here, public static void main string args, and then I create a integer object that equals to 8, and then I print it all. It's the same. And remember, in Java it is managed by the garbage collector. You have no way to access the size of each integer, each data inside your program. So that's basically it. Remember, every object is a stack pointer pointing to a heap object. That's it. References and pointers. Pointer to the heap. This is what I talk about. Java took weight off of your shoulders and put it on your legs, remember? So in Java, every function is passed by value, never passed by reference. Except for one exception. It's not even an exception, it's just a unique edge cases. So we have this code right here. Pass by value to print integer, so function. We pass the integer directly to this one. The only exception, object. Objects are first-class citizens. Remember, they are pointer to their respective heap object. So in a function, passing an object will still pass by value, but for objects, the value will be a reference. Remember, a pointer to the heap. So the one who will be passed is not the heap object, but instead the pointer to the reference to the heap object. So you can modify the object, you are passing to the function directly. But you cannot change where the reference is pointing to, only modify the value the reference points to. So we have this code right here. This print task passed by value, but we pass the reference typo right here on a mistake, I'm sorry. And then a function taking the reference of a string, because string is an object. And then we loop and print them all. So that's basically it. And then we have the object header. This is Java tags. No struct, only object. That's how it is in Java. Manually setting your own getters and setters. However, there are some taxes you need to be aware of. Every object has a header, usually around 12 to 16 bytes, consisting of marked word and class word. The marked word is basically deeply related to the Java virtual machine. It stores data related to and used by the JVM. This can change depending on the state and JVM behaviors. It consists of synchronization or locking information, basically a mutex for the Java world for multi-threaded programs. The information stores the locking and handles synchronization for threads. And then we have garbage collection, metadata, like how many sweeping garbage collector cycles has to survive, and etc. And then we have identity hash code. In Java, the memory address is useless since garbage collector rearranges things often. But identity hash code is a unique identity for each object. It shows what object this is, not where, but its identity. And then we have the class word. This is a pointer to the object metadata, basically a pointer to the information of class. Public, static, type of class, etc. That's basically it for the object header. And then we have pointer, arithmetic, and error decay, which doesn't exist, so it's a no. Remember, no pointer, arithmetic, and array decay, which of your shoulders on your legs. Pointer arithmetic is a jump of size of data type. So basically, jump how many bytes according to your data size to the next value. So accessing array E is just dereference array plus 1. Dereference the location of the array plus size of element. And in Java, memory is not static, it constantly changes. Even if you somehow get an address of a variable, we don't know when it'll get invalid. So yeah, no pointer arithmetic at all. So in Java, you don't do pointer arithmetic like C or operator overloading like C++. Instead, JVM has a special instruction that runs on every single access to get the correct data. But isn't that slow? Oh, so let me explain this something like. So in C, you just do pointer arithmetic, and in C++, you just do operator overloading. But now, in JVM, there's a special instruction which I don't know. I didn't find it at all, but just remember it has a special instruction. But that runs on every single time you access an array. But isn't that slow? Remember, just-in-time compilation. Java loves optimistic compilation, and the just-in-time compiler is smart. If the program proves it will never reach out of bounds, it skips the checking and goes straight to the machine code, in which pointer arithmetic in machine code. You don't have that in the interpreter, but in the machine code you have that one. And as a closing, remember what we talked about. Pass by reference for pass by value, which is the reference to the object. An array is an object, so we pass the reference to the array to the function. That is basically it. Create a new integer object on the heap, and this is not allowed. Arrays are full-blown objects, and it can be created in stack. And then we have we pass in the reference to the array, and after that we print that one. Yeah, this is basically it. And the last closing is error handling. In C, you have to use p-error, return, exit, hell with no clean way to do error handling. And if there's no error handling, your program will only crash or exhibit undefined behavior. In Java, we have exceptions. If the user requests an index larger than the array size, it will trigger array index out of bounds exception. If you access a null object, null pointer exception. And also, there's also multiprocessing and multithreading, but it's later, alright? So, during this busy week, I managed to write these 2 notes, and yeah, after this recording, I will chill a bit and maybe write stories, since last week I didn't write any fanfiction chapters, yeah? But that's for it. As for now, I will rest. So, Bernardus, signing off. Thank you for watching my video, and see you next week.